Right, topic 17, higher level equilibrium. Kind of two parts to this. We are going to be looking at some more KC calculations, and then we're going to be having a look at relationships between delta G and equilibrium constants. So we'll do the KC calculations first. We'll start with a hopefully straightforward one. So if we're dealing with a Haber process, we're looking at nitrogen reacting with hydrogen to form ammonia. You can write a KC expression, which is going to be that over that. And I've got the equilibrium concentrations. I'm just going to put those in, which is going to be 0.1 squared over 0.2 times 0.4 cubed. And if we work that out, 0.78, and the units would be moles minus 2 decimeters 6. Right, now in the real world we don't get usually all those concentrations neatly laid out for us. We have to maybe deduce some of the ones that we haven't got. So here I've got some information on what's going on at the start. So I've got 1 mole of this at the start. It's being heated up. There's my container volume. The mixture is found at equilibrium, so this is my start number of moles. What have I got at equilibrium in terms of moles? Well, I've got 0.114 of iodine, and I had none of these at the start. So I need to get these values so I can then work out concentrations and then work out Kc. So if I'm forming 1 mole of iodine, I must be forming 1 mole of hydrogen as well. So the number of moles of that would be the same. How much of this is left? Well, 2 moles of that give me 1 mole of this. And I've made 0.114. So that must have come from 0.228. So how much of that original 1 is left? Then that's going to be 0.772. I then need to know my equilibrium concentrations. So I'm going to divide each of those by 20, number of moles divided by volume, and then I'm going to put them into my Kc expression, just like I did in the first example. I think it turns out here that the volume doesn't really matter, because it would have cancelled out. Put the numbers in, and then you can solve for Kc. This step here, this kind of logic step, that's the hardest part of questions like this. Now, if, as it says here, Kc is tiny, in other words, your reaction mixture is still mostly reactants, you can make an approximation. And as we do calculations in the high-level acid section, this approximation is very, very important, that your initial reactant concentration is essentially the same as what you've got at the point of equilibrium. So what that means is, if I was to write a Ka expression for this, which would be CH3CO2 minus H plus over CH3CO2H, like that, I can simplify that down, because this and this, whenever I get one of these, I get one of these as well, which would mean they are the same concentration. So it's like having H plus squared on the top. Now our approximation is that this is essentially not changing, so that's going to be 0.2 because so little of it dissociates, and I'm told my Kc value, which is 1.76 times 10 to the minus 5, or Ka in this case because it's an acid, and I can solve that for H plus, which is 1.87 times 10 to the minus 3, and you'll see in a later unit that pH is equal to minus log 10 of H plus, which means that my pH, if I take that concentration of H plus ions, my pH is going to be 2.73. So it's a means of working out a pH. Okay, one more example, and we'll use the same kind of table construct to work out the missing bits. So we'll start off with what's at the start in terms of moles. At the start I've got 2 of that, I've got 1.5 of that, and I've got none of that. What have we got at equilibrium in terms of moles? Well, I'm told it's got 0.2 of that. So, how do I deduce what these were? Well, that's a 2 to 2, 1 to 1 mole ratio. So if I made 0.2, I must have used up 0.2 of that, which means it's going to be 1.8. And this one here is 1 to 2. So that means my 0.2 would have come from 0.1, which means what's left there is 1.4. I then need my equilibrium concentrations. So I have to divide each of these by the volume of the container. And then I'm going to take those and put them in my Kc expression, which is SO3 over SO2 times O2. And that's going to give me my Kc value, which I'm not going to work out. Right, so spontaneous change. You saw in the energetics unit this idea of delta G. We're looking for a delta G to be negative for a spontaneous reaction to occur. And we're going to take some of the ideas there and link them in with other stuff that we've already covered. So spontaneous change is one which, left to itself, proceeds in a definite direction to a finish. And a key thing in all these discussions is going to be disorder, entropy. Right? That's the ultimate driving force behind these reactions. So something we also have to consider is energy, and this energy is being spread out into many different little thermal microstates, and it's essentially lost, and we can look at that an example here. So if I pick up a, book, if I pick up a book, then I'm using up some of the chemical energy that's in my body to raise that book off the ground. The book now has potential energy because of its position. And if I drop it, then it suddenly starts moving, and it has kinetic energy due to its motion. Once it then hits the table, kinetic energy goes to zero because it stopped moving, but that energy needs to be transferred somewhere, and so it's going to be in thermal motion of atoms in the book and the table. And that thermal motion gradually gets spread out over all these many millions of microstates across all these different atoms, and suddenly it's no longer available to me. Right, that energy is gone, and that term for that is heat death. So my energy there has just been dissipated and lost, and is hard for me. I can't get it back. It's impossible to get back because it's gone across all these microstates. So defining entropy used to, in the middle of the 19th century, be thought of just simply as energy gone to waste. We now need to talk about this idea of thermal energy spreading across all these different states. Used to very simply be referred to as a degree of disorder, and you'll maybe still have cause to think about that when you're deciding which has greater entropy. But the key thing is the total entropy is made up of two factors: the entropy within the system and the entropy within the surroundings, or going into the surroundings. So this, the entropy within the system, you've been able to work out in topic 15, where you'll have had absolute entropy values and you've worked out the entropy change for a reaction. This, however, is harder to measure, because if you imagine you've got your reaction vessel here, whether it's a beaker or whether it's your polystyrene cup, something like that, you're able to sort of see what's in there and able to work things out. However, if we've got this disorder spreading out across all these microstates around in the surroundings, it's much harder to work out. However, it's being essentially caused by heat exchanges, and so as a result of that, if we start to consider enthalpy, then we're able to take into account the entropy change in the surroundings. So as a quick example, if you consider the freezing of water, because in terms of entropy, if I'm taking my liquid water and I'm making it into solid, then we wouldn't expect that to happen, because it's a large decrease in entropy. Things are becoming much more ordered. Right? Those water molecules are becoming more ordered, so the entropy level is going to drop. However, as it's doing that, heat is given out to the surroundings. Right? It's an exothermic process, which means that all that thermal energy is increasing the disorder, if you like, in the particles around. It's spreading into those new microstates, and overall we end up with a positive delta S total. So freezing of water is possible. This is a derivation that takes us from this idea of entropy being made up of these two terms to the Gibbs equation. And it starts by linking enthalpy and entropy. You can see them there. And then you can follow through the quite simple algebraic steps to end up with that. So when free energy reaches its minimum possible value, net changes come to a halt, and this is equilibrium. And you can see that there. So when delta G is 0, we can say that the reaction is at equilibrium, and we can also say that the entropy must be at a maximum. And depending on whether delta G is greater than or less than that 0, it's going to affect which way our reaction moves to reach that point of equilibrium. Here's an equation that links the Gibbs energy to our rate constant. And you can see, if you were to plug some numbers in, you can see that a negative delta G, which we've said is kind of a spontaneous reaction, corresponds to a positive K, which means we're going to be looking at mostly products. When we're with a delta G of 0, our K value is going to be 1. It means I've got both reactants and products in large amounts. It's kind of that balance point at my equilibrium. It's positive, I'm still mostly at the reactants because my equilibrium is over to the left-hand side. So when we're doing calculations with this, we just have to watch out for one thing, because the units of R are that. I know we usually use G in kilojoules per mole, but we want to be using it in joules per mole. So we can just plug the numbers in. So my delta G is minus 10, but remember I want that in joules per mole, so I'm going to multiply that by 1,000, equals delta G is equal to minus R times T times natural log of K. And I rearrange that and I solve it for K, and my K value comes out to be minus 55.2. Sorry, plus 55.2. That makes more sense, because if we've got a negative delta G, we're looking at spontaneous reactions, so we'd expect to be heading across to the right hand side. So there's my equilibrium constant being greater than 1. Right, we can also link kinetics to the equilibrium unit, because if we take this rather simple reaction here, it's reversible, so we can be thinking of moving in both directions. So the rate of my forward reaction, assuming it's just a bimolecular process, is that. The rate of my backward reaction is that. So I've got these two rate constants, and if I'm at equilibrium, then these two terms must be the same. Right, rate of forward is equal to the rate of backward. So rearranging that, you can see that I can tie it in with my equilibrium expression here, and ultimately it means that Kc is the same as the rate constant of the forward reaction divided by the rate constant of a backward reaction. So we've linked the equilibrium constant to rate constants. And what does that mean? Well, if I increase the concentration of reactants, we know we've got more collisions. The rate of my forward reaction is going to increase. You have to be careful just to remember there that these terms aren't going to be affected by the concentration, but we've got more collisions, so I get a faster rate, which means I'm moving quicker in that direction, so my equilibrium shifts to the right. However, the Kc is remaining the same because these terms aren't changing. If I was to put in a catalyst, both Kf and Kb benefit from that. So Kc ultimately is unchanged. So this is kind of proving something that you learnt in the standard level section. And if I change the temperature, because the rate constant is related to the activation energy by this equation here, then it's going to be affected differently depending on whether we're talking about the forward or the reverse, because they have different activation energies. So if we're changing this, then it means we're going to be changing the equilibrium constant. If we look at that here, this is an exothermic reaction. You can see that my activation energy for the backward is considerably bigger than the forward reaction. So if I was to increase the temperature, it means that rate constant would be more affected than for the backwards would be more affected than the one for the forwards, and as a result my value of Kc drops. My equilibrium is shifting towards the left. Right, so we can see that temperature will affect the value of Kc. Okay, that's what we've covered.